Hi, everyone. I hope my sound is clear for all. I'm Dr. Haidar Khan. I'm the chair for this session. This is session 7, which is natural ventilation and its role in thermal comfort. And first, I would like to welcome you all. And I need to remember you that this session is recorded and every paper has 15 minutes to be present. So first thing is, my sound is clear, everyone?
Yes, Dr. Haidar, it's clear.
Yes. Okay, thank you. So shall we begin with the first paper, which is paper 80, Users Assessment of Personal Fans in a Warm Office Space in Brazil. This paper is done by Maria. So Maria, can you begin, please?
Yes, thank you. Just a second. Just close some things that
You can present through the green button, share screen down.
yeah. I'm just not finding the paper directly. Just a second, please.
Okay, take your time.
Yeah, how it is.
Good.
Can you see it?
Yes, I can.
Okay. Then okay, thank you. So thanks for the opportunity for presenting this work. I will be presenting users' assessment of personal fans in warm offices in Brazil. The context of this work is the proposition of using of personal conditioning systems in office spaces. This type of system allows us to adjust the thermal conditions to individual preferences. This way, we can adjust the microclimate around the person and its occupancy zone and extend the temperature of the room, allowing also to achieve some energy savings. In this context, there is a lot of different types of personal conditioning systems that have been studied in the last 10 years more frequently. And for this study specifically, DES fans were chosen because in warm conditions, they seem to be one of the most efficient equipment to condition people in this kind of spaces. However, the approach used here is considering that design issues can hinder the usability of the equipment. So when we want to achieve a better thermal condition for the occupants and the extent of set point temperature of a cooling system, we have to assure that this usability won't be a barrier for its use. So previous studies shows that we can have some noise problem regarding the use of fans. Also, that the maximum airspeed that the equipment can achieve can also limit the acceptable indoor temperature of a room. The rotation, the vertical rotation of the equipment is also important if we consider that there are some spots of the body that we can direct there to reach a higher effect on the whole body thermal sensation. And also the size of the fan and its shape can limit the effect on the maximum surface area that we can reach. Therefore, the main goal of this study was to identify the most important criteria that users find on choosing a specific kind of fan, and which of them could hinder this usability. Also, the idea behind this is that we could, with this information, guide design improvement and the selection of this kind of devices for implementation in workspaces. And to do this, the study was based on an experiment in a controlled space. The experiment was performed in this kind of spaces with 4 people at the time, and they were asked during this experiment to use 4 types of fans during a similar period of time, and the conditioning of the space was changed during the experiment. Initially, we had like a dead band. Then the fans of the HVAC were activated, and at last the cooling system was activated with 26 set point temperature. At the beginning of the experiment, they were asked to fill in some personal information in a questionnaire, and at the end, they were asked to assess these 4 fans by comparing them. Also, while the experiment was run, we were measuring air temperature and relative humidity. These were the 4 types of fans that they were assessing. They were chosen regarding their differences in control opportunities, like the speed level. They had different types and numbers of speed level control. Also, the maximum airspeed of each of these equipment was different. The sound power was measured in a laboratory space, and they had also different dimensions, which is related to also the airspeed and the surface that could be reached by the equipment. And they have also different aesthetics. And the last equipment, the D, was an evaporative cooling device. So it was slightly different from the others. The participants were chosen to be like a very heterogeneous group. We have 40 participants, almost half were women and almost half were men, slightly more men than women. And they were separated by age groups, as you can see here. And also their BMI, their body mass index was calculated afterwards with their anthropometric data. And we can see that there was more people classified as having a normal BMI than the other 2 categories. And this was the main indoor air temperatures and relative humidity. We had like high, but not the highest temperatures that we can reach here is this region of Brazil. And also we had an average high relative humidity inside the room. So the initial results that I'm showing right now compare what were the previous willingness of the participants to use fans in their workspaces. And most of them tend to use air conditioning in their workspaces, and indicated they would prefer to use more natural ventilation. But there is a small sample that indicated they usually use fans or prefer to use fans. And at the end of the experiment, we asked this question again: what do you prefer to use in your workspace? And we can see here that the experiment had a positive impact on the participants. A large group indicated they would like to have natural ventilation with fans, and a new group that wasn't included in these other graphics indicated they would be able or prefer to use desk fans with the air conditioning on. And this is very interesting because they weren't usual to have this control mode, and they were considering this to be a preference at the end of the experiment. The other important thing is the criteria they consider the most important. So this graph shows the rating of the criteria, which they found most important. And we can see here that the top two are related to air movement and speed adjustment. This was expected considering we are accessing fans, but also they indicate as the third most important noise level. And we can see here rotation is an important aspect, and also financial aspects were considered important too. And when we consider this criteria in this last overall assessment, they have a great relationship. We asked people to rate these 4 types of equipments regarding this criteria. Best, which one had the better sensation, better thermal adjustment, was quieter, and has the better aesthetics. And we can see in all or most of the criteria, the option D was best rated. But in this, regarding the noise, the option B was best rated. We can also see the option A doesn't appear in any of these graphics, so it wasn't considered the best option in any of these criteria. And later on, we asked if you had the chance to use one of these equipments, which one would be? And as it shown in the first graphic, people have half of the people preferred option D, and it had like a similar tendency for preferences regarding option B and C initially. But when we talk about purchasing an option, this tendency regarding B and C changed a little bit. And when we include the prices of the equipment, as option D was like 40 times more expensive than option B, only one person was willing to pay this price. And we can see here that the number of people that prefer to purchase the option B increases a lot, as it was even more less expensive than option C. So this shows that price is very important when considering a purchase situation. But if the owner is giving them the equipment, maybe they would really prefer option D. So this would change if the owner of the equipment is the user or not. And then to better understand this situation, we did a relation to regarding this last choice, or the almost last this choice, disregarding the prices, with the anthropometrical data. And we can see here some tendencies, like regarding the age, we can see that younger people prefer D and B, and less people prefer option C, and older people seems to prefer a little bit more like option C than B. Regarding the gender separation, we can see that men have a very equally preference, regarding these three options, while women do prefer option D more often in this sample. And also the other part prefer option B. There is a small part of women that preferred option C. And regarding the BMI, we can see we had like a lot of people in the normal category. So most of them preferred option D or option B, and a lower number preferred option C. We established some statistical analysis and couldn't find any.
Sorry, you have 1 minute only. Please finish. Sorry.
Okay, any statistical tendencies regarding the anthropomatical data. So we can affirm that option B and C could be applied to office spaces much similarly. So to wrap up, we found out that controllability aspects are very important on the definition of this type of equipment and their design. Also, higher speed wasn't considered so important as it would be expected, and people preferred like a smooth and controllable wear. The noise produced by the equipment is very important to be considered, and financial aspect can be eliminatory criteria if the occupant is also the owner of the equipment. And the possibility of using desk fans with air conditioning wasn't like a usual condition for participants, but they consider this as a good opportunity at the end of the experiment. So we think like they have to be exposed to more options of control and control modes to be able to use that option too. And future work, we will consider activation drivers that were included in the experiment. And we are also doing energy savings potential analysis in another article regarding the use of personal fans. So thank you very much. And if you have any questions, I will be glad to answer.
Thank you, Maria. Can you close the sharing, please?
Yes.
Thank you. And now let's begin with the second paper, which is paper number 11, an investigation of the natural ventilation effect in CO2 concentration in Nepalis school buildings. So, Mr. Nishan, can you begin, please?
Yes, sir. Are you listening to me?
Yes, it's on display.
It's my screen share to you. Is it okay? Sorry. Hello, everyone. This is Mishan Shrest from Tokyo City University. I'm a PhD second year student at this university. Today, I'm going to present my paper entitled An Investigation of the Natural Ventilation Effect on CO2 Concentration in Nepalis School Buildings. I hope this presentation will let you know the current situation of CO2 concentration and ventilation associated with indoor air quality in naturally ventilated Nepalese school buildings. Natural ventilation uses wind forces to inlet fresh air in and dilutes indoor air contaminants like CO2 concentration, moisture, and heat. And looking back at the 2020 academic year in the world until date, we are suffering from the COVID-19 pandemic, and academic school communities were closed to reduce the risk of COVID-19. And it is said that natural ventilation could be an effective on-site sustainable mitigation strategy to be safe from such kind of disease and improve indoor air quality associated with CO2 concentration and ventilation, and improve thermal comfort of the students. In the context of Nepalis school buildings, most of the Nepalis school buildings are relying on natural ventilation. No heating and cooling systems are provided in the classrooms, and windows are the major source to ventilate the air. As shown in the pictures, you can see just big windows are provided in the classrooms. No heating and cooling systems are provided, and in those classrooms, the study of CO2 concentration and the ventilation associated with indoor air quality has not been studied till date. And most of the studies conducted in Nepal are focused on thermal comfort at residential buildings. A very limited study on thermal comfort at school buildings can be found, and no studies on CO2 concentration and ventilation are found in the Nepalese context. Therefore, to address the research gap of the indoor air quality associated with CO2 concentration and ventilation, this study was undertaken in school buildings in the temperate climate of Nepal during the summer of 2019 with the following major aims. And in this study, based on the data collection, CO2 data collection, we analyzed them. And in this study, we have developed a model, and using this model, we'll estimate the ventilation rate, number of air change rate, and we use it to estimate the CO2 concentration. And finally, we'll compare the measured CO2 concentration with the estimated CO2 concentration to check the model developed in this study. And this shows the map of Nepal, and the study was conducted in 2 districts, schools located in the 2 districts, temperate climate of Nepal's. And this diagram shows the annual monthly mean air temperature and relative humidity of the investigated areas. The hottest months are from June to September, and the temperature reaches minimum from November to January. And this study was conducted during this period, May of 2019, and 3 schools, 7 classrooms were investigated, and all schools were naturally ventilated. No heating and cooling systems were provided in those classrooms, and the students from grade 8, 9, and 10, it is grouped 12 to 18s were participated in this study. And this plan view shows the characteristics of the investigated classrooms in 3 schools in 7 classrooms, and occupancy of the students were different classroom to classroom, and the number of windows also different school to school. And in this type of classroom, and we measured CO2 concentration along with temperature at 10-minute interval for the whole day periods of regular lesson using this kind of digital instrument. And in this study, we developed a model using a transient mass balance equation. And the basic principle is that the amount of CO2 going in and the CO2 emitted by the students must be equal to the CO2 stored inside the classroom and CO2 going out. And this is the very basic principle of mass balance. And using this equation, we reduced it to explicit type of equation, and we developed 2 equations, equation 1 and 2. And the equation 1 is used to estimate the time varying number of air change rate, and equation 2 is used to estimate the CO2 concentration. And for the equation 1, the time, there is a constraint for time. The time period must be very small, and in our case we took 30-second time interval. And to estimate the number of year change per hour, we used these 6 factors, like a number of students, outdoor CO2 concentration, initial indoor CO2 concentration, metabolic rate, CO2 emission rate, and room volume. And using these 6 factors, we estimated the number of year change rate, ventilation, and we used it to estimate the indoor CO2 concentration. And here are our results. And the first figure shows the temperature versus time in 3 schools in 7 classrooms, and outdoor temperature and indoor globe temperature are plotted here. And from these 3 graphs, we can see that the outdoor temperature are very close to indoor globe temperature, and the temperature increases, becomes higher at during the daytime. And in the second figure, it shows the CO2 concentration versus our time. In 3 schools in 7 classroom, we found the CO2 concentration were below 1000 ppm. And this must be because of the natural ventilation and large ventilation rates, as I explained before, that just open windows, and also the cross ventilation that may be the reasons to have such low indoor CO2 concentration. And if we compared it with the previous study, then in our case, we found a very low range of CO2 concentration in the investigated school buildings. In the previous studies, even they were naturally ventilated, CO2 concentration were found higher than 2000 ppm. And this shows the number of year change rate versus our time in 3 schools in 7 classrooms. In all of the investigated classrooms, we found more than 25 times per hour ACH. And of course, there are many reasons behind such that just I explained before. The natural ventilations, large because of large window sizes, and the cross ventilation, adequate cross ventilations, maybe the major that reasons. And the other reasons, the orientations and the architectural design also, and the occupancy of the students also have the effect on having such higher number of year change. For example, in school year 3, both classrooms C6 and C7 are similar in dimensions, similar shape and sizes, but the different is only in occupancy. In C6 classroom, there were higher occupancy in comparison to C7. The higher occupancy means it is connected with the more CO2 generation. More occupancy, more CO2 generation. So more CO2 generation indicates the ventilation rate is low. So that is one of the reasons for school yes 3. And if you compared the results of our study with previous studies, the one thing is that the method employed in our study is different than the method employed in the previous study, as tabulated in this table. The previous study used a steady state analytical methods, but our is different, a time variant, a number of year change rate is estimated in our study. The methods are different. However, on comparing with the previous study, our study shows the very high ACH and the CO2 as well. And it was very surprising to us. But when we reviewed the previous studies, few studies also found the similar kind of results based on the natural type of ventilation, cross ventilation or single site ventilation. And for example, in one of the study conducted in Nepal, found up to 73 times per hour ventilation, number of ACH in the traditional houses. And in China, in a multi-story hospital, when they used the cross ventilation. The number of air change rate was found up to 160 times per hour, but it was different when single site ventilation is used. And using the estimated ventilation rate, we estimated the CO2 indoor CO2 concentration, and we compared it with the measured CO2 concentration, and result is presented as shown in this figure. And this figure shows the estimated CO2 concentration versus measured CO2 concentration. And this shows the fitting of the estimated CO2 to the measured CO2 concentrations is close, verifying that the model developed in our study is working well. And this model can be used in the future for further study and analysis. And here are our conclusions. And the measured result showed that the indoor CO2 concentration were within the acceptable limit. And this shows that the Nepalese school buildings have the potential to provide appropriate indoor air quality that associated with ventilation and CO2 concentration. And the ventilation rate was higher than 25 times per hour. And this showed that the investigated classrooms, Nepalese school classrooms, have the potential to provide adequate ventilations during the summer season. However, for the winter season, it may not be suitable for the students. Such high ACH or ventilation could be a problem, could be problematic to the students. Therefore, for the winter season, we need to investigate in the future. And last, the estimated indoor CO2 concentration fit wall with the major CO2 concentration. This confirmed that the method developed is accurate for the estimation of CO2 concentration and ventilation analysis. And in overall, the findings of this study should be useful for the evaluation of naturally not only the Nepalese school buildings located in the climate similar to Nepalese school buildings should be useful for the evaluation of the indoor air quality associated with the CO2 concentration and ventilation. And this is good for all of us to rethink the role of natural ventilation for the energy use or indoor environmental issues. And thank you very much, Kai, your kind attention.
Okay, thank you, Mishan. Please, can you close the sharing? And let's begin with the third paper. This is paper 36, Shelter Indoor Environment and Health, Measuring the Impact of Shelters on Health Worldwide, presented by Anna.
Thank you.
Anna, just the sound, if you can drop
Yeah.
it, please.
Can you hear me?
Yes, I can hear you very well.
Thank you. So good morning, everyone. This is Anna Conzatti, second year PhD student at the University of Bath. And today I would like to present my paper, Shelter Indoor Environment and Health, Measuring the Impact of Shelters on Health Worldwide. The background of this project is the indoor air quality and thermal comfort in refugee.
Sorry, Anna, there is echo in your sound.
Yeah.
There is echo in your sound.
Can you hear me?
Yes, I can hear you, but there is a strong echo in your sound.
Okay. Sorry.
Okay.
The background of this project, as I said, is the indoor air quality and thermal comfort in refugee shelters. According to the last UNHCR report, more than 79 million of people are currently displaced around the world due to armed conflict or natural disaster, and often these populations are encamped in temporary shelters which provide poor indoor conditions in which to live. For example, shelter indoor temperature are about 40 degrees in summer, while an apparent temperature of 25 degrees represent comfortable conditions. The image from a recent study of FOSSAS showed the distribution of UNCHR people of concern living in shelters and distress, and it's evident that the majority of households living in shelters are subject to high level of heat stress. However, heat stress is only one of the risk factors that jeopardize refugees and IDPs' health, because, for example, harsh climatic conditions, lack of wash facilities, and poor shelter quality are important determinants of health, especially in the case of displaced population, where these factors contribute to the development of specific health disease, such as airborne disease, hypothermia, gastrointestinal disorder, cardiovascular issues, and injuries, all of which result in a reduced life expectancy, especially for children under 5 and the elderly. From a preliminary review of the literature, has been clear that very little has been done to address the link between shelter and health. Therefore, a bibliometric and systematic literature review followed by a comparative review has been conducted. And the results of the bibliometric review have shown that there are 4 main clusters of research concerning shelter and health. Existing literature has also observed that shelters are fundamental determinants of human health, and they present some issues related to certain health disease. For example, overcrowding was mainly related to sleep deprivation and in general any infectious disease, and air quality was related to respiratory infection, which represent a threat, especially for children under 5. Very little is known about the relationship between extreme temperatures in shelter and health. Shelter generally consists of a single room where all the activities take place, such as cooking and sleeping. Therefore, indoor air quality can be poor due to the presence of cooking fuel or dust, and moreover, due to low airflow rates and the lack of pipe or chimneys. All of these factors determining poor air quality are also interdependent. Little has been done to investigate indoor air quality refugee shelter. Existing studies have mainly focused on the impact of cooking fuels using inside shelters without considering the role of shelter design and the relationship between indoor air quality and ventilation. The work I'm presenting here is the preliminary stage of a more complex project analyzing the shelter design and indoor air quality. So firstly, the shelter model were constructed and then co-simulated using building software simulation. After the validation, the impact of existing shelters on health has been measured. And then new approaches to ventilation will be selected and used to create new retrofitted models of shelters on the base of the existing ones. And this new model, again, will be co-simulated and validated, and their impact on human health will be measured. And finally, the outputs regarding health impact of both cases will be compared and analyzed, and the results will be summarized in a shelter guidance. For this preliminary study, shelters in Nistat refugee camps have been monitored for 15 days. Temporary shelters constructed in Nistas were rectangular shaped and constructed with hollow concrete blocks walls and corrugated galvanized iron roof. Both the door and the window on the same side had CGI shutters and were usually taken closed during the night due to the fear of theft and security reasons. Furthermore, due to the lack of overhanging shades over windows, some families had to close the windows during the day to avoid direct sunlight inside the shelters. Therefore, they reduced the amount of airflow inside the shelter. And this study assumed that the window is open during daytime and closed during nighttime. Because windows were kept closed during the night, ventilation rates were assumed to be approximately the same as infiltration rates. The study focused on ISTA's refugee camps because shelter is in that area were highly overcrowded and refugees used to cook indoor using traditional charcoal stoves several times during the day. And they use also to shut windows during night and occasionally during nighttime. Besides, the camp was exposed to the hot desert climate and refugees reported living in discomfort. Therefore, CO2 has been measured for 15 days, and during the field work has been observed that poor level of air quality were mainly due to cooking fuels, dust, low airflow rate, and absence of pipe and chimneys. These two last factors are the most important when investigating the impact of shelter design on human health. The ideal procedure for obtaining a comprehensive analysis of indoor air quality involves recording all the indoor contaminants concentration through the use of sensor and the direct monitoring of pollutants emitted by the source of cooking. However, in that case, owing the unpredictability of field work in refugee camps, such as limited access time and mistrust in monitoring equipment, these procedures were too expensive and not adapted in extreme locations as for refugee camps. Therefore, a simplified approach using ventilation effectiveness to identify the acceptability of indoor air could be suitable when working in displacement settings. So the study was performed using CO2 indoor concentration due to occupancy as a proxy of ventilation rate. Then, through the use of building simulation, it was possible to construct a model of the shelter in ISTAS, predicting the shelter behavior in terms of indoor air quality and pollutant concentration, and as well thermal comfort. So preliminary results show that show a comparison between two shelter models, so the control shelter and the shelter with an improved airflow. And the control shelter show that shelters do not provide the minimum air exchange to maintain the maximum permissible CO2 concentration level as per ASHRAE, so it's 1,000 ppm. Therefore, occupants are exposed to excessively high levels of indoor pollutants, and they are potentially exposed to indoor air-related health issues, especially during nighttime, when the windows are shut. However, as can be observed from the orange line, by applying simple design improvements, the airflow can be enhanced and the levels of indoor pollutants reduced. For example, by increasing the airflow rates during the night, seems to be one of the possible solutions to reduce the indoor concentration of CO2 and provide a healthier indoor air quality. To provide higher ventilation rates, it would be possible to maintain the window open during the night, preserving security and privacy of refugees, for example, by adding a net or a steel bar to the window. The use of building simulation to analyze the indoor air quality presents some advantages. Firstly, building simulation is cost effective and provides the flexibility to evaluate different design and material alternatives for the same model. And this is advantageous, especially in the field of shelter design. However, this study presents some limitation, mostly related to the building simulation, which is an uncertain science. Simulation results, in fact, depend on the input data, which in the case of shelters may be difficult to find. And as well, estimating the airflow rate from carbon dioxide concentration may be problematic, especially for naturally ventilated dwellings, as ventilation rate is affected by several environmental parameters. And additionally, finding a link between a particular shelter design to specific health disease is challenging due to the lack of information about households and health status. Finally, future studies should continue to investigate the role of CO2 concentration as an assessment of ventilation. And in refugee settings, future studies should include the study of indoor pollutant resulting from indoor cooking using solid fuels, which are well known to be a threat to the human health. And therefore, future direction should investigate more deeply the impact of shelter design on indoor air quality, also considering thermal comfort. Thank you for your attention.
Thank you, Anna. Can you please close the share? Now we will end with the paper 19, which is evaluating the energy saving potential through occupant interaction with the external fenestration in residential building. And this is presented by Amanda. So Amanda, can you begin, please?
Yes, I am going to share my screen. Is it visible to you?
Still, now it's okay. Now it's visible.
Okay. Well, a very good afternoon to all of you all. I'm Amanda Santiago, and my topic is evaluating the energy saving potential through occupant interaction with the external fenestration. I was guided by Professor Rajan Raval from CEPT University. In today's presentation, I will be covering a context to give you all a bit of understanding of the climate that we were up against, the aim and objective of this study, an extensive literature review, followed by the methodology, and then the analysis and results, and finally the conclusion. In India, buildings account for 35% energy consumption, of which 20% is from residential buildings. Bangalore has a comfortable indoor environment through natural ventilation for most part of the year. The chart alongside is from the National Building Code's IMAC model. It's derived from there. As you can see, the portion in white is the area fit for natural ventilation. Now, despite Bangalore having a comfortable indoor environment, the study goes deeper to understand why people in residential homes in Bangalore keep their windows closed for most part of the year. Knowing the climate of this space, the purpose of the study was to investigate the occupant operation with the external fenestration and to identify the thermal and non-thermal drivers that influence this operation. What kind of drivers are we looking at? The thermal drivers are basically our environmental factors such as temperature, humidity, and air quality. The non-thermal drivers are non-environmental factors, which basically poses a hindrance while opening your windows. That's pest, security, air pollution, etc. An extensive literature review was conducted of nearly 35 papers, from which it can be known that occupants have a profound effect on the indoor climate and energy consumption of a building. The crucial point lies in the fact that occupant behavior cannot be determined. However, a set of common tendencies can be observed. In 2011, Anderson et al. Conducted a survey from which they understood that it is necessary to have the indoor and outdoor conditions be known while trying to understand occupant behavior, and hence data monitoring is necessary. In 2017, Yao and Yu conducted a study from which they also included data collection plus the survey, and they understood the importance of monitoring the window status. There are various ways in which the window status can be monitored. In 2013, Anderson et al., they used a magnetic induction strip to determine the status of the window. However, the extent to which it was opened could not be determined. This was overcome by Adhoc in 2014, in which he used image capturing to determine the window status. However, the learning from his study was that when the blinds were closed, the window status could not be determined. In 2015, Chu and Cohen used CO2 tracer gas to determine the ACH and find the status of the window. Our study uses a similar experiment. There have also been various complex simulation models to estimate and predict the window opening. Our model is rather simple and only focuses on the possible savings that can be adapted from this study. The methodology followed is basically of three broad categories: the online survey, a field study consisting of data monitoring, simulation, which allows us to find the ideal period for when people can open their windows and a possible energy saving by them doing so. Now, what can be understood from this methodology? I'll describe each in detail. First is the survey. The survey was developed by a strategy. The survey was online in nature. It catered to 18 years and above, and it was restricted to the location of Bangalore in India. It reached out to 150 to 200 people. While developing the questionnaire for the survey, there were filters that were put into place, followed by the house and window characteristics, the past behavior of the occupant, barriers that the occupant faced, and preferences of the occupant. While conducting the survey, it was ensured that the survey was in English for a duration of 10 to 15 minutes, and prior to the survey being sent, a call was placed, and also a reminder 30 days after. On entering the data, it was known that filling the form was completely voluntary, and the data recorded was recorded in the form of a Google Sheet. Now, the outcome of the survey was mainly to understand the thermal and non-thermal drivers, mainly to identify the non-thermal drivers on a large scale. The next stage was the field study. The field study consisted of two parts: data monitoring and experimental stage. The data monitoring consisted of indoor parameters, outdoor parameters, and window status. The indoor parameters included the dry bulb temperature, relative humidity, and occupant-generated CO2. The outdoor parameters had the dry bulb temperature, relative humidity, and air quality. In order to determine the window status, the experimental stage was used, in which CO2 tracer gas experiment was used as a proxy to determine the opening percentage of the window. The outcome of the data monitoring was to verify the thermal drivers that influence the opening, and also the experimental stage outcome was to define the window status. This window status was put into the simulation model. The final stage of the methodology was the simulation. The simulation was done in two cases. One, which was mainly based on design builder's differential temperature variation algorithm, and the second, in which the operation schedule was based on the opening data collected on site. The opening data collected on site was of three categories: active user base, passive user base, and mixed user base. Now, the inputs for the simulation model, the building materials, were taken for the GBPN report. The lighting power density, equipment power density, and schedule was taken from the data collected on site. The importance and the outcome of the simulation was allowing us to identify the ideal time in which people could open their windows, and also the possible energy savings in them doing so. The data monitoring. As you can see, monitoring was done in bedrooms of 9 homes, which is a total of 18 rooms. The bedrooms are considered based on literature review, in which it was found that occupants interact the most with the windows in their bedrooms. As you can see, the sensor data loggers were used to collect data of the occupant-generated CO2, the Hobel logger, which was also placed in the bedrooms, as well as one outside to get the ambient conditions. In addition to this, the data from the nearest weather station was collected, and the air quality from an open source Purple Air Logger website was taken. These, which were taken online, were ensured that it was within a kilometer radius from the site. The experimental stage. The experimental stage was conducted to understand the status of the window. These were the windows that were considered. Various opening percentage of these windows were identified and placed in time of doing the experiment. The experiment was done in many stages. At first, all windows were closed, the fan was switched off, and no occupant was allowed to enter into the bedroom. Then the source was brought into the room. In this case, it's a CO2 cylinder. To ensure, after opening the CO2 cylinder, the concentration of the room was allowed to reach 5,000 ppm as per the ASMT guidelines, after which the source was taken out of the room, the fan was switched on to ensure circulation, ensuring 5,000 ppm was maintained. Finally, windows were opened and the decay was observed. This decay was then matched with the occupant-generated CO2 that was collected daily. Now, to verify if the ACH that was collected, we use the Lekaware guide to calculate the ACH. As you can see, the measured and the calculated ACH varies between 2 to 5 ACH. On verifying the ACH, the schedule for all the 9 houses, that's the 18 bedrooms, was plotted. The schedule was taken into 3 main categories: active user base, in which occupants open their windows a lot; passive user base, in which occupants hardly open their windows; and mixed user base, which was a combination of active and passive. Now, on understanding the energy savings that were possible, these were put into the simulation model. The base case was designed with the temperature variation algorithm, from which we achieved 72 to 86 comfortable hours. As you can see, there's been a reduction on comparing it with the passive, mixed, and active user-based. Now, in order to understand what could be the thermal drivers in this kind of a situation that led to the reduction in comfortable hours, we did an ANOVA test to understand the relationship of the opening with the outdoor temperature and humidity, and no significant relation was found. The same was done for the indoor conditions as well as the air quality of the outdoor, but no, there was no significant relation, which brings us to understand that this is why the non-thermal drivers come into play. Now, to understand these non-thermal drivers, 150 people were surveyed, of which 90% of them operated their windows themselves. 51% of the surveyed people preferred opening a window than switching on the fan or the air conditioner. Out of the people surveyed, most of them had an independent home. At least 50% of them had one window in each space in their home. To understand the non-thermal determinants, it can be seen mosquitoes posed as the problem for most homes, followed by dust. However, these determinants varied from time of day. As you can see, insects and mosquitoes pose as a problem during the evening and night, whereas security and air pollution pose as a problem during the day. I will conclude with what I started. Bangalore, located in India, is a temperate zone and has a comfortable hours for nearly 50% of the time. However, occupants do not take advantage of this climate, which results in 20% additional uncomfortable hours. In order for people to achieve their comfort, they tend to switch on a fan or an air conditioner. This increases their energy cost by at least 30%. It's a clear cycle. The way people operate their windows is directly related to the energy they consume, which directly increases the finance that they spend on the same. People in Bangalore pay a penalty of increasing their energy cost by 30% because of the non-thermal drivers that prevent them from opening their windows. Thank you.
Thank you, Amanda. Please, can you close the sharing?
Yeah.
Now, let's begin with the questions. And first question to Amanda, please, can you close the sharing?
Yes, I am trying to.
Okay.
Is it? Yeah.
Thank you. So let's begin with the question. And first question is to Maria. Now, Maria, in your work, did you consider the draft effect?
We had like an additional questionnaire during the experiment that wasn't analyzed yet. They were answering like instantaneous thermal comfort questionnaire during the experiment. So these results that I have shown, they only consider the initial and the last questionnaire applied. So the other variables were not included in this study yet. And the questionnaire does include not draft directly, but it includes the thermal comfort, acceptance, and other variables like preference for air movement and so on.
Also, Maria, did you consider other body parts like the face, like the neck? You know, the higher part of the body usually sense the thermal comfort or the air velocity much higher than the rest of the body. So did you consider that as well?
Yeah, we tried to measure the airspeed in different parts of the body, like positioning it close to the person. And so we had like 4 points that were measured during the experiment that also would be processed and analyzed afterwards.
Okay, last question. Why didn't consider ceiling fan? Ceiling fan is something common, especially in Middle East.
Yes, but you cannot reach like a personal control with ceiling fan usually. There are some ceiling fans that can be like individualized, but desk fans have this ability that they can be movable and directly controlled by one occupant in a shared space. I'm specifically interested in shared office spaces, so that for the desk fans were selected.
Okay, thank you. Now,
Thank you.
I have a question to Anna.
Yeah.
Sorry, just a question.
Sorry.
There is another question here in the chat. Should I answer it by writing or can I answer it by speaking? Sorry.
Okay, you can answer it by both ways if you want.
So just a quick answer here. The Home Badur, I don't know how to say it, sorry, asked me if we did consider the relationship between acceptance and comfortable ranges regarding the airspeed. And yes, we will be analyzing this afterwards also. We did like a lot of questionnaires during the experiment. So we want to see the relationship, cross relationship between comfort and thermal comfort ranges and airspeed also. Thank you.
Okay, thank you. I hope that question been answered. Now, for Anna.
Yes, thank you.
Okay, I have a question. It's about the validation. Did you?
Yeah.
Okay.
So yeah, for validating the model, we need to compare the concentration of CO2 obtained from the simulation with the CO2 monitored during the 15 days of field work. We need to finish this part as for refugee camp was not possible to monitor the shelter for 24 hours. And usually for validation, it's better to have a 24-hour monitor to compare with the data obtained for simulation.
Okay.
An idea is also to, in that case, model the thermal behavior of shelters and compare also the temperature obtained from the simulation with the temperature monitored in the shelters. Because in that case, we have continuous data for more than 2 weeks.
Okay. By the way, did you consider only one climate? I think it's like hot arid climate, yeah?
Can you repeat the question, please? Because the audio is not very good.
Okay. Did you consider other climates?
Yes. So, in that case, I just simulated the case of Ethiopia, but I'm considering to analyze as well the case of Nepal and the case of Peru. So yes, Actually, I will concentrate just on extreme climate, but maybe interesting as well to simulate in extreme cold climates to see if there is any interdependencies between the temperatures and the CO2 concentration. Some previous studies, but not in shelters, but in common buildings, have found that actually there is an interdependence between temperature and CO2 concentration. So it would be interesting to simulate using different climate conditions.
Okay. Do you think in simulation for COVID in the future?
Yes. I think it would be a good way to also project better buildings and to have the possibility to see how a build can behave under certain condition, also in terms of occupants' behavior, because building simulation allows the possibility to simulate as well the occupants' behavior in terms of opening and closing the windows. So it will be very important to add this tool when project buildings and airflow, especially now after the COVID pandemic.
Okay, thank you. I have a question for Mishan. Mishan, are you there?
Yes, sir. I'm listening.
Mishan, in your experiment, did you change the location of the device?
Yes, thank you for the question, sir. Yeah, we did not change the location of the instrument. We fixed it at the center of the classroom at the morning time. For the whole regular lecture period, we set up the instrument at the fixed point at the center of the classroom.
But the student must in the center or the end of the class? Because usually in the classes, all the students will be concentrated at near the wall at the end of the class. So did you test that thing?
Sorry, sir, I did not listen to your question.
Because the student usually sit at the end of the classroom, near the wall at the end. So I think there will be higher concentration at the end of the classroom for the CO2 concentration.
Concentration of, you mean positions?
Of the CO2. Because there are many students there, so the air quality there will be less than the center.
Air quality less at the center.
Okay, yeah. For future, if you can try to test different position for the device and see how that will affect the reading, it may be a good idea. Also, the device is calibrated. This device that you use it is calibrated, is scientific device or is commercial device for the CO2?
Yeah, that device our previous seniors also, that devices has been used. These devices that made in Japan, and that was calibrated in our lab with the other devices.
So you calibrated among other devices, and it's fine.
Not that sensei. We use the same with the similar device sensei. We did not use the other devices. That because the device that we have used is very costly in comparison with the other devices, and our lab also recommended this kind of device.
Okay, thank you.
The measurement of CO2 concentration. Yes, sensei.
Now I have a question for Amanda.
Yes.
Amanda, there is a question from the chat from Dr. Shaham, and it's about the advantage of design builder.
Yes. So I will take that question. So design builder is easy to use. The user interface is very quick to pick up. That's one of the prime importance. Also, it's very fast. You can do complex models in quickly than the other softwares. The drawback to design builder, however, I would say, or the learning would be, it's a paid software, so probably that's why people are hesitant. And in addition, like when you use other softwares, I think Builder gives you an advantage with the ease.
So Design Builder is used in Energy Plus, yes? Like other
Yes.
software,
Backend, yes.
like Open Studio or something
Like
that.
Open, yes, exactly. Design Builder has Energy Plus backend.
Yeah, but the good things about Design Builder, it includes CFD model as well.
Correct. Yes,
But
it does
did you
include.
consider to use
No,
it in
I did
future?
not. I did not do a CFD model for this
Okay,
study.
but for future, did you consider to use it?
I've not thought of, but it can be. I mean, there are a lot of things that still have to be looked into from my side with regard to the CFD part in Design Builder.
Okay, thank you. And also you use ANOVA, where the data normally distributed.
Yes, the data was normally distributed. It was for all homes. It was, yeah, it was collected and correct, normally distributed. Or we also, before the start of it, were to remove the outliers and the basic things were done.
Okay, thank you. Dr. Hong, do you have a question, please?
Yeah, okay, thank you for your presentation. So I'd like to have one question for Amanda. I think you said the window opening and the air temperature and the humidity,
Correct.
I think you didn't find significant difference, right?
I did not find any significant relationship between them and as to if people actually open their windows because of those thermal drivers.
I think you have done, I'm very surprised by that one.
Yes.
The reason might be because I think you just did a measurement in January, February, and March, isn't it?
Mm-hmm. Yes.
I think because it's a cold season, and that's
People
why
tend to,
maybe
yes.
the people, they are not controlling the window. But if you do the survey in the full year, so
I probably
whole
see some.
year, and definitely you'll find some relationship here.
Yeah. Also, I did review the kind of data that I got with the occupants and not particularly asking them, but trying to understand when they generally open windows. So I noticed that a lot of them, the non-thermal drivers were an important part, like the noise or the mosquitoes, that they preferred switching on the fan than opening. Their first instinct was to switch on the fan than opening a window. So that was something even in the houses in which the data was recorded, I observed.
So for example, if the, maybe the, in terms of temperature, maybe it's too obvious. Maybe everybody is controlling. Maybe they are not answering because it's too obvious for them. For example, if you observe the window opening, if the temperature goes increase, and definitely you will find the window opening percentage, or maybe they also opening.
Yes.
Right?
Yeah.
I think
That's
so.
Something I can
Slightly
look at
surprised
doing.
because of the heating season, I think.
Yes.
Okay, thank you.
You're welcome.
Thank you, Dr. Hong. And by this, we reach the end of section 7, and we'll have a break for 15 minutes. Then in 12:35, we'll begin with the keynote session. Thank you all for interesting subject, and see you in next conferences.
Thank you.
Thank you.
Thank you. Bye.